symbolic. Where we introduce the wave function and the energy expression. So now let's do a sample problem. A few sample problems. Alright, so as we said in quantum mechanics, all the dynamic information for the system is contained in the wave function. Once we have the description for the system, then we can predict a lot of those properties. I'm showing here some examples. We can calculate the average positions, right? The average of the square of the positions. We can calculate energy. We can calculate linear momentum, so on and so forth. But the idea is the same. Now, keep in mind, when you calculate those properties, we need to know the system in what kind of state. Because the system can be in a variety of quantum state. So therefore, those values will not be the same. All right? So now let's say we can use the simplest one, the quantum state, that is the ground state. So let's use an example. So the quantum state is denoted by the V. So if it's a ground state, we know the V equal to 0. Now we know the general expression, guys, for the wave function. It's a variable x. We say it's motion in x dimension, right? Now that expression has 3 components. One is your normalization constant. Then the second component is your polynomial function in a substitution of using y. But y is not the axis, okay? Y is just a substitution, so don't get confused. And then you have the third portion, where your wave function is this Gaussian function. It's an E function. Okay, so those are the 3 components. Now the x and y are related. I mentioned they substituted x with y to make this expression much easier to evoke. All right, now the alpha is a constant that equals to alpha is related with your mass of the oscillator and the spring constant. Okay, now x is our variable. I can keep writing. Then the range is from the negative to positive range. Alright. Okay, so in that case, now let's say the system is the ground state. Now can we calculate the average position? Right. Can you guys predict what would be the average position?
The expected value.
Average, right? The system can be in different locations. So what if you sum them all up? What would you guys think? Huh?
The middle?
Middle means what?
0. 0. No, it's fine.
0 means equivalence, right? Now let's see if that's true. Okay. Alright, now, what is this notation, guys? What is the bracket?
It's vector.
Huh?
Vector notation?
Okay, that's what I was saying. The same symbol in different subject mean different things. In quantum mechanics, the point bracket means
Expected value.
expectation value. Okay? Now, what is the expectation value? It's an average value or mean value. All right, now how we're going to calculate the expectation value is already given here. You're going to have an integral of that complex, it's the product of the whole thing. So you have a complex conjugate of your wave function times the operator here. Now in our case, our operator is the position operator. Okay, so maybe let me take a step back. Let's do this. If a particular observer that I'm interested, a general expression will be like this. Operator will operate onto your wave function, and then you integrate with the allowed space. All right, now to be complete, we do also have the denominator component. That is just the integral of the wave function, the complex conjugate. Now, if the wave function is normalized, then the denominator will minus 2, 1. Okay, now the question for us is, for the harmonic oscillator, are those wave function expression normalized?
Should be.
I would say yes. Why would I say yes?
Oh.
Because I have the normalization constant right there. Oh, I should have. Okay. Yep. All right. Okay. Now let's apply. So we're interested in the average position. Now, what is the position operator, guys?
X.
Position operator is just a variable in our axis, and it is a multiplication. Okay, so now let's plug it in. So I'll plug it in. This is x from the negative infinity to positive infinity. Now the wave function. Oh, that's another part is, what will be our wave function? Let's write out. So the wave function will be equal to 0. Then you have a corresponding normalization constant when d equal to 0. Now we have an expression how to derive the normalization constant. Maybe I'll flash that out. Right here. So the normalizing constant also varies, depends on which quantum state the system is at. Okay, so it has a different value. But right now, I'm just carrying, say, a equal to n sub 0. I can give you exact expression, but I don't want to make my integral expression so complicated. Just use the n sub 0. You can plug in v equal to 0 into the normalization constant, and you get the exact expression. Okay, maybe I'll put that stuff up right now. All right, now how about the h function here? When it's 1. And then we'll have the Gaussian component. But I want to do an integration. You can use an integration with the substitute y, but I want to make it simple. I just want to in terms of x. So in that case, your normalization constant times, so y equals x divided by alpha. So I can substitute this here. Any questions on that? So I just figured out is the quantum state, b equal to 0, ground state, figured out each 3 components, and then although the expression given to you in terms of y, but my variable is x, so I'm going to return back to the x. Now there's a couple things I can do. This is alpha. Alpha is a constant, and this is a 2, number 2 right here. So I can do a little simplification here. So this will equals to x squared 2 alpha squared. Okay, so this is my wave function. Now, before I do the integral, this or all of the harmonic oscillator are real function or complex function? Real. They are all real functions. They are all real functions. Okay, now let's plug it in. So right here, so I will have the normalization constant. Differentiating. So it's an integral. So I have limits, upper low limits with respect to the variable, that's your x. I plug it in the wave function for the ground state, then follow this expression for expectation values. Now, what do you guys think this value going to be? Of course, I can take it a step further. So this is a complex conjugate of a real function that equals to
0.
itself, right? Yeah?
Yeah.
And then I have this and this is exactly the same. Now what do I have? And this is a multiplication. So therefore it will become squared. Do you guys agree with that? Okay. If it's a square, if I take it further, it's a product of 2. So therefore it will be the square for the constant. Then you have a operate onto this e function. Then the 2 will vanish. Almost anything, it's just algebra right now. Okay, now I don't really need to have this guy right here. You know, so basically I have a constant squared, have an e function, I have an x, and do the integration. Is this odd or even? Even. And you multiply by x, would that make the whole thing adds up? Odd. Okay. Which means I don't have to do anything. Use the math, I want to know this equals 2. And then I integrate from the negative symmetrically from negative infinity to the positive infinity with an odd function that will give me oh yeah. Yes, guys? Okay, so that's where if we think about their math involving tricks, and that's where it kicks in here. So therefore, sometimes it sounds like it's a dumping integration. But if you remember from your math, you integrate from the negative to 0, 0 to positive with an odd function that cancels out. But if it's an even function, that becomes twice from that, from 0 to infinity. So that will give you, or you can go home and take a shot at this. I'll plug it in if you wish. Then I can use the normal, given to you integral that from the textbook and try it. But if I would definitely, when you do integration, think about this even on a property that will eliminate a lot of lengthy mathematic problems. Okay, so that tells you the position. The average position is when it's 0, right? 0. Okay. Now how do we do? All right. Now, how are we going to do the average for x squared then? We follow exactly the same thing, except now your operator, it is, if you want to figure out the average for the square of x, now what you need to do is you need to generate the operator. It's really nothing fancy. Now, what will be the operator? It's just position operator. It's just a multiplication. So therefore, it's an x squared. So therefore, what you're going to do, you're doing the exact same thing. Either expectation value, generate expression, plug in your wave function, it's a real function, so it will become your squared. Right here, you'll have the corresponding operator that is x squared. Now, if that's the case, will this even or be odd?
It should be even.
Right? This will be even, right? If it's an even function, there's a mathematic trick you can use. Is if I integrate from the negative end to the positive end, can you guys follow me okay? I can integrate from 0 to the positive, and that just 2 times. Hey, I saw some of you smiling right now. What are you smiling about? Are you happy about this?
Wish I knew it in Calc 3.
What's that?
He wishes that he knew it in Calc 3.
Oh, I see. You guys don't talk about Calc 3?
No,
No.
Oh.
they want to make your life as hard as possible.
But that's the whole point of Calc 3 is to prove that. Now, after you prove that, you can apply to it. You don't, in my class, you don't need to prove that. You just borrow it. So once you set up this integral, you say, okay, it's an odd function, and from negative to positive, and if it's a 0, I'll definitely take it. I will be happy, smart. You know, I don't need you to prove that. Okay, now how are you going to take out this integral? I have an equation sheet in the resources. Remember we talked about this resources, it's the math resources, and then you can use it from there. Okay? Alright, now, the reason I'm telling you this is sometimes we forgot. And I just want to use this example to show you we can use some tricks, make your calculation much easier. Okay, good. Alright.
Yeah, I don't remember what it's at. Even when I
Alright, now let's keep going. Now we said, okay, we can obtain the position, and the square of your position, whatever. But we also can calculate energies, right? How are we going to obtain energy values? Now, the expression for the energy at given quantum state is denoted. So there's a wave function expression. Now we have energy expression, E sub V. So that equals to the quantum number V plus 1/2, then times H bar omega. Okay, now omega equals to the root of K over the mass of the operator. K is your spring constant. Okay. Now, what is omega here, guys? What do we call this omega?
Angular momentum? No.
Who said angular momentum? Who said no? Okay, you guys with Ben?
This is a different
Yeah.
Angular frequency.
Angular.
Okay, so
You were halfway.
no, I like this discussion. That's good. Okay, so the angular frequency. Alrighty, so this is the angular frequency for the angular frequency for the oscillator. Do you guys agree with that? That is the same that subjective for the vibration. Alright, so I'll just remove that as long as you guys remember. So this is the angular frequency for that oscillator. Can we convert it to the normal frequency?
Yes.
Yes.
So
Okay,
2
then
pi.
raise the width. Okay, then this is your normal frequency. They're linked together. Alright, but that is the frequency for the oscillator, subjective for the oscillation. Okay. Alright, now, this is from the Hamiltonian operator, solving for the Schrödinger equation, you have this energy expression. That energy includes 2 components, right? What are they?
Kinetic energy and
The
potential.
energy includes 2 components. What are they?
The kinetic and the potential.
The kinetic energy, of course, at that particular quantum state. So it's the sum of the kinetic energy and plus the potential energy. Now, for the particle in the box, the potential energy inside the box is 0. But in this case, the potential energy from a harmonic oscillator is not a 0. Do you guys agree? Yeah. So therefore, the sum of the kinetic energy and the potential energy equals to the total energy. Now, how are we going to calculate each one of the components? We are going to introduce this theorem. This this theorem says if the potential energy only works under the conditions, if the potential energy of the particle has the form when the potential equals a constant A times A raised to the power B, then it means its mean potential, the average potential, and kinetic energy are related. Okay, now can we take a shortcut? Can we take a shortcut to that? So this theorem says if the potential energy has an expression of a constant times the position difference of the power B, then the average kinetic energy and average potential energy can be correlated. So how that be correlated? If that's the case, then 2 times the average value for the kinetic energy equals the constant B times the average for this potential energy. Now let's evaluate what this theorem applies to our harmonic oscillator. Okay, now we need to evaluate. For the harmonic oscillator, what is our expression for the potential energy? We said it's a parabolic, right? So the thing is satisfied with the Hooke's law. The force is the negative kx. Force is really the derivative of potential over dx. And therefore our potential energy expression is 1/2 k times x raised to the power 2. So that is the expression for our potential energy. The reason I just told you is a harmonic oscillator. So the force is subjected to the Hooke's law, which is proportional to your displacement with the constant of your spring constant. Now, in physics you learn the force is the derivative of potential energy over the x, and then you can derive the v by do integration of f dx, and that's how we derive the expression for the potential energy. Okay, now let's come back. With an expression like this, does it satisfy with the theorem?
Yes.
Yes? Yes? Okay, if it is, then what is our v here? So in that case, then the theorem said if it satisfies with this, then the 2 times of your average kinetic energy equals to b times the average of your potential energy. What is our b here?
2.
Is this power, right? So the theorem said a constant. Yes, we do have a constant right here, 1/2 k. Have an x raised to the power 2 raised to the power b. The b for our case, b equals
2.
b equals 2. Yes? Okay. Is it Friday today?
Yes.
What do you guys want to do after that? Not after that.
Movie in the bar.
I told you last weekend is homecoming weekend, right?
Yeah.
I said I had a horrible something to hear. Everyone said, yes, I want to hear this. I've had a fever around 2 days of a fever. You know, it's terrible. Otherwise, I'll go to the homecoming, so on and so forth. When I was a graduate student, I don't know. Yes, I didn't attend undergraduate year. The instructor always tells us to have fun, right? So that's not good. All right, we already studied. Okay, so what does that mean? That means based on this theorem, we have a shortcut. So there's a relationship between the average of what? They're exactly the same. That's beautiful. Why is that? Because I have an expression for the total energy. If I want to calculate the average for kinetic energy or potential energy, right? that equals to, so in this case, if I'm asking, can you give me the average or expectation value for the kinetic energy or potential energy if I know the state for the system plug A to B equal half of that total energy? Does that make sense to you? Okay, now what if I forgot about, I don't know about this theorem. If I don't know about this theorem, how I'm going to calculate expectation value for potential energy? How I'm going to do it? I'll do the same. What I'm going to do, I need to come up a potential energy operator that equals to 1/2 k squared. Then what I'm going to do, let's say if I want to do, I need to plug in the operator with 1/2 k squared here. Are you guys following me okay? I can also calculate the average for the potential energy using generic expression. How to calculate that? So I'm interested in the, the average for the potential energy. I need to generate the operator. I will plug it into this expression, and I have to do the integral. Why take these lengthy steps when you know it directly in this case? So for the harmonic oscillator, because satisfied for this theorem, you really do not have, I mean, of course you can do it if you like it, go with that one. You'll get exactly the same answer. Are you guys following me okay?
Mm-hmm.
Okay, in that case, I want you to tell me what would be the value for the average kinetic energy or the potential energy for the system at the ground state. I mean, you can do the integral right there. That will give you. But if I want to take a shortcut using the theorem, so for the ground state, so this is a quantum number, ground state. So E at the ground state equals
We have the ground states equals
1/2. Because that's your expression. The V equals 0. So that will equals 1/2. Not until everybody nods their head and I'll continue. Does that sound good? Okay, now what about our
1/4.
Very good. Now check. You can go through this integral, see if you get 1/4 h bar omega. They should get you exactly the same thing. There's not really nothing wrong to start from the general expression. That sound good? Alright, so same problem, you have a multiple approach. Okay, now I'm going to erase all of those. I want you guys to draw the potential well for the harmonic oscillator. Alright, and then within that potential well, draw the energy. Will you do that? So draw the potential well for this harmonic oscillator.
let's see potential low.
Oh, we can do it together. Right. So you have axes. your x-axis. So the y-axis is your potential energy, and the mathematical function is the potential equals 1/2 k x squared. And then you can plot it here. That is your potential well. Right? And then this v approach to negative infinity or positive infinity as x approach to the positive and negative infinity. So this is your potential well for the system. Okay, now I'm going to erase this. So at this middle is x equal to 0, that is your equilibrium point. Okay, so that is your potential well. We know the mathematical function we plot with respect to your x variables. Everybody get that? Now I'm going to do some changes. So I'm going to erase the x variable. I'm just keeping the potential well. Now I'm going to impose the quantum state with energy. So the energy starts from b equal to 0, b equal to 1, b equal to 2 for the harmonic oscillator sits in this potential well, right? So at the ground state, where the energy corresponding to? It's not at 0 at some places. You guys agree? So that is say corresponding to, oh, it's tilted. That equals v sub 0. All right, now the energy is increasing. Right, this is our energy expression. For a particular oscillator, omega here is a constant. H is a constant. It varies with the quantum state. Alrighty, now for the next level, I just keep going. And we talk about this in now, what is the spacing between these two guys?
They're equal.
Huh?
Equal spacing.
Equal spacing? Between those two neighboring states? Are they equal spacing?
Yes.
Yes. Oh no. Let's try it. Let's give it a shot. So how are we going to calculate the energy differences? We're going to calculate the energy differences between those two neighboring states. Now, we can say two neighboring states is b plus 1 and b, between those two, right? The importance is they varies by quantum number 1. That's why it's in neighboring states. You guys follow me okay with this? Okay. Then we can calculate the differences of delta E. That is between the quantum states with a higher one versus with a lower one, vice versa. But I'm just using one as an example. Okay. All right. Now we know the expression right here. So this will be b plus 1. That's your quantum state. Then plus 1/2 h bar omega, then minus the state for energy with v equals to 1, so v plus 1/2 h bar omega. So all I did is just a simple substitution, okay? So you want to calculate the differences between two quantum states. I know the expression for each quantum state, then I just put it in with the specific quantum state. So they are neighboring states. So if one is v, the other one is v plus 1, or the other one is v minus 1, it doesn't really matter, so I'm just choose one. Now, if you do this math, what will be the result?
H bar omega.
Yeah, so you have a V, H bar omega, V, H bar omega, you have half to here. What you really have is so the difference is we talk about this when we talk about energy, but I just proved to you again for the system, and that's why the spacing are equally spaced, because the difference is equal to a constant. Alright, now I'm not done yet. Okay, now the question I'm having is if I have a system transit between one quantum state to the other quantum state, or neighboring quantum state, okay? So let's make it clear. So now, okay, if the system transit between those two neighboring quantum states, how are we going to derive the frequency of the light? So we can have the system hopping from low to high, you need to absorb, or from higher to lower, then you can, emit light, right? You guys following me okay? Yes? Okay. So basically, I have this two neighboring quantum state. I can hop back down. Then what will happen is, as I'm jumping, as the system jumps from the highest state to the lower state, the excess of energy will be released as light. Okay, now how are we going to do this? Then I need to satisfy with the Bohr frequency conditions. Should I say Bohr? So there are energy differences in your system or the particle. It has to equal the energy of the light, whether it is absorbed or released. And we have done this before. Now, except that we're going to apply this to our vibrational motion. Any questions with this? It's too easy. I can speed up. The one thing I'm good at, I can speed up.
No.
Can we continue? Okay. Now, what is the energy difference for the system between two neighboring states? Wait, what do you guys think?
H bar omega.
Okay, so it's H bar omega. Okay. That is written in terms of the angular frequency. We can also write in terms of what? Normal frequency. Who can tell me? If I want to write in terms of normal frequency for the oscillator, what would be?
2 pi u.
2 pi H V. It's 2 pi H V.
Right? Right. Because the omega and the normal frequency are linked by 2 pi, and the H bar and the H is linked by 2 pi too, so they cancel out. that is, I have a frequency because it's oscillating for the particle, has an angular frequency, also has a normal frequency. That differences from your system has to equal to
Energy of the
the
light.
light. How can we calculate the energy for the light?
Got one away.
The energy for the light is a photon. And the light is a photon. How do you calculate energy for the photon, guys?
Is H over C or
That's H.
H?
If the energy of your photon equals h times nu, but here nu refer to the frequency of the light that is absorbed. Yes. Now, don't confuse, we have two frequencies here. One is the frequency for your oscillator. The other one is the frequency for your light when you have a transition. Now, what kind of expression can we conclude? If the system hops between two neighboring quantum states or vibrational motion, two neighboring quantum states, then the frequency for the oscillator, the normal frequency for the oscillator equals to
Frequency of the light.
okay. Sorry. Seriously? You just go through one slide? Only one slide. Only one slide. Now we were talking, no, I can't let you go. I'm looking forward to see you guys, right? Because the rest